In this video I'm going to draw some diagrams, and when I draw a diagram like this, so here is a set X, and then an arrow, and then another set Y, and then with an F like this. And when I say F is a function from X to Y, what I mean is that F is a function whose domain is X and whose codomain is Y. So that's the meaning of this diagram. So let's suppose we have another function, G, this time with domain Y and codomain a third set, Z. So in this case we can produce a new function with domain X and with codomain Z, whose rule is do F and then do G. And that function is going to be called the composition of G and F. And we're going to write this composition in a particular way. So the composition of G and F is written G circle F, or sometimes just GF like this. And its rule is as follows. So the rule is G composed with F at an input little x and big X is what you get by applying G to what you get by applying F to X. So we could summarize this in words by saying that the rule for the composition of G and F is do F, then do G. Okay, let's see a very quick example of this. So we might have, for example, the function F from Z, the set of integers, to the set of natural numbers, given by the rule F of X equals X squared, and we might have a function G from N to N, given by G of X equals X plus 1, and then we have F going from Z to N and G going from N to N, so we're able to form the composition as I've described it earlier. And G composed with F would go from, well, what should happen? It should start off and have the same domain as F. So it should go from Z, which is the domain of F, to the codomain of G, which is N. And its rule should be that G composed with F of an integer X should be G of F of X. And in our case, F of X is X squared and G of X is X plus 1. So in our case, this would be X squared plus 1. Right, and this emphasizes that it's really important to get this the right way round. It's important to remember that G composed with F means do F first and then do G, and not the other way round. It's quite easy to get confused about this. But really, if you think about it, the only natural interpretation of G circle F is do F, then do G. And the reason for that is because we write the argument to a function on the right of that function, right? We write F of X. We don't write of X F. That's not how we choose to write things. So because we choose to write the input to a function on its right, the only natural interpretation for G circle F is the function which does F first and then do G. So that's why when we write G circle F, we mean the function whose rule is do F first and then do G. Okay, let's look at a more complicated situation involving function composition. So we're going to consider the situation where I have three functions. So here F is going to be a function from X to Y, and G is going to be a function from Y to Z, and H is going to be a function from Z to W. And in that case I can form two different compositions, because I can look at the composition of H with G composed with F. G composed with F is a function from X to Z, so I can compose that with H. And I can also look at another composition, which is H composed with G composed with F. again, this makes sense because h composed with g is a function from y to w, so I can compose that on the left with f because f is a function from x to y. So both of these two compositions here and here, those things make sense. And it's quite natural to ask the question, are they actually equal to one another, right? They're both functions whose domain is x and whose codomain is w. And we could legitimately ask the question, are those two things equal as functions? And in fact, the answer to that is yes, they are equal as functions. And that property is called the associativity property for functions. So I've written it just here as a lemma. The lemma is called composition is associative. And as you can see, what it says is that if we're in the situation that I drew a diagram of just now, where f is a function from x to y, g from y to z, and h from z to w, then the two compositions, h composed with g composed with f, and h composed with g composed with f, in fact, are equal. So I remind you, I've written the definition of equality of functions at the bottom of the screen here. This is the definition that we wrote down in our previous lecture, and it told you that two functions were equal if and only if they have the same codomain, the same domain, which I'll call x, and if for every element of their common domain they have the same output for that input. So if I want to check that these two functions are actually equal, then what I have to do is check those three things hold. And in our case, well, they certainly, both h composed with g composed with f and h composed with g composed with f, they certainly have the same domain because that domain is x, and they certainly have the same codomain, namely w. So if we're going to prove this lemma, we're going to first observe that the first two parts of the definition of function inequality are definitely satisfied. So both h composed with g composed with f and h composed with g composed with f have domain x and codomain w. So the first two parts of the definition of function equality are satisfied. What we need to do is check whether they have the same output for every input in their common domain x. So let's just work out what their output is given an element little x in the common domain x. So we'll let little x be an element of big X, and we're going to figure out what both of these two compositions do to little x. So h composed with g composed with f, evaluated at x. What is this? Well, we have to use the definition of composition. So the definition of composition applied to this composition here tells us that we obtain this, the output, by doing h2 g composed with f applied to x. Okay, we'll use now the definition of composition again, and using the definition of composition on this composition of g and f, this is h applied to, g applied to, f applied to x, like this. Okay, and that's the best we can do. We can't simplify this any further because these are completely arbitrary functions, h, g, and f. We don't know anything else about them. So that's the best we can do. Let's now try the other composition. So if we now look at h composed with g, and we compose with f applied to x, then again, unwinding this inner composition here, what happens? Well, by definition of composition, this is h composed with g applied to f applied to x. And then again, just unwinding this remaining composition, what we've got is h of g of f of x. Right, the same thing that we had before. So these two things, if you look at them, they are the same, and so for every element of their common domain, the two functions h composed with g composed with f and h composed with g composed with f have the same output, and so we've checked all three parts of the definition of function equality, and we're done. We've got the same output for every input, and so these two functions are genuinely equal. So that's the end of our proof. I'm going to draw a little square to indicate that I've done with this proof. Okay, one more thing to think about then before we move on to a new slide. We talked before about the associativity property in a different context. We talked about associativity of unions and intersections of sets, and we established that unions and intersections were associative. And when we did that, we looked at a second property, which was the commutativity property. So we showed that set union, for example, was commutative. If you have two sets A and B, then A union B and B union A are equal. So it makes sense to ask about function composition. Is function composition commutative? But we have a bit of a problem because, in general, if you've got functions, so let's say f from x to y and g from y to z, so that you can form the composition g composed with f, that makes sense. Well, the problem is that you can't even form the composition f composed with g. Right? It doesn't make sense to form the composition the other way around. So you cannot think about f composed with g in this context, because what that's supposed to mean is the function whose rule is do g and then do f. But once you do g, you've got into the set z, and you can't apply a function f whose domain is x to an element of z, right? In general, z and x might be different, and you can only evaluate the function f on elements of its domain. So this doesn't even make sense. So we can't even start to ask, is f composed with g equal to g composed with f? So that's a bit of a problem. And in fact, if you think about it, the only time when f composed with g and g composed with f could possibly be equal would be in the case where f and g both go from a set x to itself. So let's now observe that even if we're in this situation, so even if we have a function f and the function g both going from a set x to itself, it may be that f composed with g and g composed with f, which this time are legitimate functions and have the same domain x and the same codomain x, well, it still may be the case that they are not equal. So you will look for examples of that yourself on a problem sheet. Anyway, in short, the commutativity property doesn't apply to function composition. Okay, last slide is about composing with the identity function. So I'm going to remind you of the definition of identity function. If you have a set x, then the identity function on x is defined as a function from x to x which does nothing. So the identity function x at an input little x equals little x. That was called the identity function. And what the lemma here says is that if you compose a function with the identity function on either side, then it doesn't change that function. So if you have a function f from a set x to a set y, then f composed with the identity and the identity composed with f are both just equal to f again. So let's briefly see why one of these equalities is true. So proof, let's do this first equality here. So again, I've written at the bottom, I've reminded you of the definition of function equality. Two functions are equal if they have the same domain, the same codomain, and if they have the same input, the same output for every input in their common domain. So if we observe that both f and f composed with the identity on x have domain x and codomain y. So they do meet the first two conditions for equality of functions. And what we now have to do is check that they meet the third condition for equality of functions. So let's say, furthermore, let's take little x to be an element of their common domain x. And then if I look at f composed with the identity, and I evaluate that at x, then what I get, by definition of composition, is f of the identity of x. Okay, but the identity of x, the identity applied to x is just x again. That's what the identity function means. Okay, so what we see here is that f composed with the identity and f both do the same thing to an element little x in big X, namely they send it to f of x. And therefore, let's just end the sentence there. So f and f composed with the identity meet the three parts of the definition of equality of functions, and so they are equal. And we're done. There's my little square to indicate that this proof is finished. Now, if you want to check the other equality, just, where am I? If you want to check this equality, then you can do that, or you can look in the type notes.